today we will look at applying systems of linear inequalities with linear programming. The definition of linear programming: a method for solving problems in which a quantity that must be maximized or minimized is limited by other factors. Note to self: one of the most widely used tools in management science. It helps businesses allocate resources in such a way to maximize profit. The objective function is the algebraic expression in two or more variables describing a quantity that must be maximized or minimized. For example, bottled water and medical supplies are shipped to survivors of an earthquake by plane. Each container of bottled water will serve 10 people, and each medical kit will aid 6. If X represents the number of water bottles, that's important, so we probably want to highlight that. So X represents the number of water bottles to be shipped, and Y represents the number of medical kits. We're going to write the objective function that models the number of people that can be helped. So objective functions, typically we will use the letter Z. I need my pencil. And then equals. So if we know nope, we can't write it yet. Whoops. Never mind. Reread the problem. Note to self also, it says each container of bottled water will serve 10 people and each medical kit will aid 6. So those are key things we need for our objective function. So like I said earlier, we use the letter Z for our objective function. 10 bottles of water, so that would be 10x, since x represents the bottles of water, plus medical kits will aid 6 people, 6y for number of people. For constraints, these are restrictions in the linear programming problem. So it says each plane can carry no more than 80,000 pounds. Okay, so that's critical. The bottled water weighs 20 pounds per container, and each medical kit weighs 10 pounds. Okay, so that goes in with our yellow because we're talking about pounds. Each plane can carry a total volume of supplies that does not exceed 6,000 cubic feet. Okay, so that's also critical information. And each bottle of water is 1 cubic foot, and each medical kit has a volume of 1 cubic foot. So that's going to go in green because we're talking about volume. If we wanted to write our constraints, we set up a system of inequalities. Because we cannot have a negative number of medical kits and bottles of water, we are restricted to quadrant 1. So we're going to include x is greater than or equal to 0 and y is greater than or equal to 0. Okay. Now we can use our underlined information. If I know the bottled water weighs 20 pounds, well, that's 20x per container for number of containers, and y 10y. Remember, no more than means I cannot go exceed 80,000 pounds. So we'll use a less than or equal to sign. Okay. For our volume equation, it says each bottle of water is 1 cubic foot, so that would be 1x, and each medical kit also has a volume of 1 cubic foot, that would be plus 1y. And together it cannot exceed 6,000 cubic feet, meaning we cannot go over 6,000 cubic feet. So again, we'll use less than or equal to 6,000. When we're solving a linear programming problem, the first thing you'll want to do is sketch the region corresponding to the system of constraints. So that means you're going to graph. Then you're going to find the vertices of the region you just sketched. Okay. Then you'll use the objective function or the z equation at each of the vertices and select the values of the variables that optimize the objective function. In our example, we wanted to know what is the maximum number of people that we can assist. Okay. And just in general, for bounded regions, both the minimum and maximum values will exist. For an unbounded region, if an optimal solution exists, it has to occur at a vertex. So if we go back to our water bottles and medical kits example, notice we have our objective function and we have our constraints. If we look at the key words, notice it says determine how many water bottles and how many medical kits should be sent on each plane to maximize the number of earthquake victims who can be helped. Okay, so that means when we test our vertices, we will want the largest value. Okay. When we go to sketch our graph, we're going to ignore the objective function just for right now. Okay, so this is gone for right now. And remember, we want to be only in Q1. So that's why on your notes and on these slides, there is only one quadrant. Remember to sketch the second constraint that we wrote. It's a linear equation, so remember we have to solve for the y variable so it's in slope-intercept form. In order to do so, we're going to subtract the to the other side with the 80,000. And then by 10. Once we do so, note that we have y is less than or equal to 8,000 minus 2x. When we go to graph that, we graph our y-intercept, 8,000, and then our slope we go to the right one. Okay. I like to go until I meet the x-axis, so I know I have a close approximated point. And then because it's less than or equal to, we draw a solid line. If I look at the standard form and I test 0, 0, 0, 0, when I test it, is 20 times 0 plus 10 times 0 is less than or equal to 80,000. Which ends up being a true statement, because we essentially have 0 is less than or equal to 80,000. So that is why the area underneath the green line is shaded. To sketch our second constraint, we will follow the same process. We are going to solve the bottom inequality for y, so we will subtract the x to both sides. And again, we will plot our y-intercept, 0, 6,000. And our slope this time is -1, so we will fall 1 and move to the right 1. And continue doing so until we reach the x-axis. And again, we'll draw a solid line because it's less than or equal to. If I were to put 0, 0 into this equation, we do get 0 was less than or equal to 6,000, so we will shade underneath. Now we are ready to do step 2 to determine the vertices of the region. The vertices are where everywhere is shaded, so note to self, our entire shaded region is this trapezoidal looking area, quadrilateral looking area. And we have a vertex here, 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 and here. It's a good idea to try to graph as precise of lines as possible so you don't have to do any algebra. So we know our objective function z equals 10x plus 6y. Okay. Our first ordered pair, well, we can start here with 0, 0. And I just replace the x's and y's with the 0. And we do get 0. The next ordered pair looks like we have 4,000, 0. So we only need to do the x-coordinate. So 10 times 4,000 is 40,000. Our next vertex looks like to be 2,000, 4,000. Okay, so our z, 2,000 times 10 is 20,000. And 6 times 4 is 24, so it'd be plus 24,000. So z altogether would be 44,000. Okay. And then our fourth intersection point is on the y-axis. It is 0, 6,000. Okay. We only need to calculate the y because 10 times 0 is 0. So 6,000 times 6 would be 36,000. Okay. So now we want to find the optimal solution. If we want to know where the maximize, we're looking for the biggest z value. And our biggest z value is here, located at this point. Okay, so our final answer the max earthquake survivors that can be helped is 44,000. By sending $2,000 water bottles and 4,000 medical kits. Okay, so this would be our final answer. So typically what I like to do is I like to circle it, and our assignment to